Welcome back to the deep dive. We are jumping right into the thick of it today, looking at one of the most intense global rivalries shaping our technological future.
That's right. We're talking about the accelerating race for AI supremacy, particularly in large language models.
Specifically, the race between the United States and China.
It's a competition that, analysts almost always frame through the lens of pure resource superiority.
Right. Who has the most compute? Who controls the hardware?
Exactly. Who has the most massive computational clusters, who's got the cutting-edge hardware, and who has the deepest pockets of, data and talent? Those are always the big questions.
They're the easily observable constraints. But if you've been following the convergence of performance metrics between top Western and Chinese models, a convergence that has been shockingly fast, it just suggests there has to be something else.
The deeper structural factor at play.
Yes, something that provides an inherent, almost unfair advantage. And today, we're taking the shovel and digging into that exact structural advantage, the Chinese language itself.
And how its logographic nature is providing a critical and actually quantifiable efficiency edge in LLM architecture.
So for you, the learner, our mission today is to unpack precisely how the structure of written Chinese, which is known as hanzi, translates into this critical computational edge.
Right, and we're going to be moving beyond just general linguistics. We're focusing strictly on the mechanics of machine learning.
So things like token costs, sequence length.
Exactly. Sequence length reduction and the resulting nonlinear performance gains you get doing both training and inference. This is really where linguistic structure becomes a form of high-level data compression.
So we're not doing cultural analysis here. We are treating language structure purely as an input encoding scheme.
No.
You're asking, what is the most efficient way to communicate a concept to a transformer architecture? And the data really seems to suggest the answer is not the alphabet.
Precisely. And if we frame this discussion in terms of computational efficiency, which is what we do here, the true bottlenecks in scaling AI are universally recognized.
Token costs.
Token costs, the limits on processing sequence length, and the demanding resource requirements of inference, especially when you're talking about real-time deployment.
So anything that reduces the input size while keeping the same informational density, that's a huge win.
It provides an immediate and substantial engineering benefit. And our sources, which include these really detailed analyses of LLM tokenizers and linguistic data, they confirm that this efficiency gain is now a major strategic factor.
Okay, let's unpack this and set the stage for the current competitive landscape. For years, the U.S. had what looked like an insurmountable lead.
Oh, absolutely.
We had the foundational architectures, the pioneering firms like OpenAI, and the benefit of building systems that were, largely optimized for processing English.
That perceived dominance, though, it's eroding. And it's eroding dramatically. The source material is very, very clear on the pace of this convergence.
What are we talking about time-wise?
By early 2026, many analysts estimate the performance difference. And this is measured through capabilities on complex reasoning tasks and benchmarks between the top US and Chinese models has shrunk to just mere months.
Mere months, wow.
And in some specialized domains, that gap is effectively zero, or in some cases, even slightly negative.
And crucially, this success isn't just hidden away behind proprietary walls. It's actually concentrated in the open source arena.
That's a huge point. Models like DeepSeek, Qwen, GLM, these are all Chinese origin models.
And they're topping global download charts, setting really impressive records on established benchmarks like MMLU, the massive multitask language understanding benchmark.
This rapid open source success is a massive indicator of scalable innovation. It forces us to look past the superficial benchmark scores.
Right, you have to dive under the hood.
You have to understand the fundamental mechanical advantages driving this newfound efficiency. And that takes us directly to the universal technical bottleneck of all LLMs, regardless of where they come from, tokenization.
Okay, so if tokens are the universal currency of LLMs, where does the English tokenization method specifically break down? I mean, in terms of carrying maximum semantic value.
That is the right question to ask. We often forget that LLMs, they're not reading words. They're performing matrix multiplications on numerical vectors.
It's all just math.
It's all just math. Text first has to be broken down into these discrete, quantifiable units we call tokens. And the vast majority of models, particularly those optimized for English and other alphabetic languages, they rely on techniques like byte pair encoding.
BPE.
BPE, yeah.
So BPE is essentially a frequency-based compression algorithm, right? It looks for the most common sequences of characters and merges them into a single token.
Exactly. The process is inherently statistical. It tries to find a balance between the size of the vocabulary and the length of the sequence. So if ing appears frequently, it becomes its own token.
But a less common word like tokenization might get split up.
It might be split into token and agotization. And the fundamental issue for English and other alphabetic scripts is that our writing system is primarily phonemic. It represents sounds. We use combinations of 26 letters to construct meaning.
Which means that even a complex multisyllabic word might still require 3 or 4 separate tokens because the tokenizer has to capture all the component sounds or subwords.
And that's the core inefficiency right there. The token is capturing a sound fragment, not a dense concept. On average, standard English test requires about, say, 0.75 tokens per word.
That doesn't sound too bad.
It doesn't, but that efficiency rapidly degrades when you're dealing with a few things. First, complex or technical jargon. Think of a word like geosynchronous.
Okay.
That might get tokenized as geosync, ro, nos. 4 tokens for one concept. It also struggles with low-frequency words or morphological complexity, where prefixes and suffixes have to be constantly represented by additional tokens.
So the model ends up having to process more tokens just to receive the same information payload compared to a system where the input is inherently denser from the start.
Precisely.
And let's put a finer point on the computational cost. Why does this matter so much technically?
Well, the cost is directly proportional to the number of tokens, which, as you said, is often denoted as n. And these longer sequences of tokens translate immediately to 3 critical and very expensive scaling problems.
Okay, let's start with the most expensive one. Computational costs during training and inference.
That ties directly into the transformer's attention mechanism. The resources needed to calculate the relationships between every single token in a sequence, the self-attention layer, that scales quadratically.
Or ON, with the sequence length n.
Exactly. So if a model processes, say, a 100,000 token prompt, and you manage to reduce that prompt to 70,000 tokens while conveying the exact same content, the savings aren't 30%.
No, because it's quadratic.
It's proportional to 100,000 squared versus 70,000 squared. That quadratic reduction represents just massive compounding savings in floating point operations.
So simply put, if you can cut n by 30%, you are saving far, far more than 30% of your computational energy. It's a non-linear efficiency game.
Exactly. The second problem is it affects inference time.
The latency.
The latency, yeah. Longer sequences mean more memory fetches, more matrix multiplications, which translates directly to slower responses for the end user. In a high-throughput production environment, think about serving millions of API calls. Even a 10% increase in latency will cost real money, and it degrades the user experience.
And the third major problem is memory demand, which is what constrains the context window itself.
This is maybe the most immediate hardware bottleneck. The full sequence of tokens, along with all the key value caches, the KV caches that are generated by the attention heads, they all have to reside in the GPU's extremely limited VRAM.
So if your text is 30% longer in tokens?
You're consuming 30% more of that precious VRAM bandwidth and space. And this either limits the usable context window, the model's effective short-term memory, or it forces firms to buy more expensive, higher VRAM chips.
Like the A100s or H100s?
The very ones which, as we'll discuss, is a sensitive geopolitical issue.
So if you can convey the same dense concept like a complex scientific hypothesis or a long legal clause in 40% fewer tokens, you have effectively solved all 3 of these major scaling constraints at the same time.
You have. It becomes a pure, unassailable engineering advantage.
It's the ultimate optimization.
It is. The inefficiency of BPE on alphabetic languages creates this constant structural drag on the entire system. The model is forced to perform these computationally expensive operations simply because the input encoding is, well, redundant in terms of its semantic density.
Okay, we've established the severe computational penalty paid by English-optimized models because of this token sprawl. This sets up the logical contrast perfectly. And here's where it gets really interesting, because we can shift focus to the Chinese language structure and its technical implications for efficiency.
Neural signal check. Here's why this development actually matters at a technical level. We need to stop viewing hanzi through a traditional linguistic lens and start seeing it for what it is: a superior input encoding mechanism for large-scale computation.
Okay.
While alphabetic languages are phonemic, constructed sequentially by letters representing sounds written Chinese, hanzi is fundamentally logographic.
And define that logographic structure for us, specifically in terms of information compression.
Okay, so each hanzi character is a logogram. This single, often very complex symbol represents not a sound, but a morpheme, which is the smallest unit of meaning, or often an entire concept.
The whole concept.
A whole concept. Think of it as a pre-compressed data packet. Critically, it packs substantial semantic, conceptual, and even historical meaning into a single processing unit for the model.
So while the English tokenizer is busy processing components, sounds like assordination or geo, the Chinese tokenizer is frequently processing a full conceptual building block in a single step.
That's it exactly. It's the difference between transmitting instructions letter by letter and transmitting an entire command using a single dense symbol. Let's expand on the sources example, the term Zhuhua Renmin Gonggeguo,
which means the People's Republic of China.
In standard written English, that concept requires 4 full words, plus any articles or prepositions you might have in a sentence.
The Chinese term is comprised of 7 hanzi characters. And in an optimized Chinese-centric tokenizer, and that optimization part is really key, that entire dense political concept is represented by just 7 tokens for the LLM.
7 tokens.
7 single units to input an enormous amount of geopolitical specificity and density. And the English equivalent, when you factor in BPE splitting up the multisyllabic words like republic and including filling words, could easily consume 20 tokens, maybe more.
It could, yeah. And the contrast only gets sharper when we look at more complex technical terms. Consider chit, meaning nuclear fusion. That's 3 characters, likely 3 tokens. The English term requires 2 full words, which might total 4 or 5 tokens after BPE gets done with it.
Give me another one.
Okay, a medical term,
Angyabing,
meaning diabetes. 3 characters, 3 tokens, conveying a very specific disease state. The English requires 1 multisyllabic word that could easily be 6 tokens.
So this isn't just about character count, it's about the semantic weight that each individual token carries. The LLM is just receiving clearer, denser conceptual instruction right from the start.
Which brings us to a crucial counter-argument that you often hear from critics of hanzi in computational settings.
I think I know where you're going with this.
If each character represents a concept, aren't there way more unique hanzi characters than common English subwords? Wouldn't that require a massive, inefficient embedding table?
That's a great point. A standard LLM vocabulary might have, 50,000 English BPE tokens, but the full set of hanzi characters is vastly larger, maybe 80,000 or more, plus all the compound words. Wouldn't that huge vocabulary just consume an enormous amount of VRAM for the embedding layer?
That's where the Chinese-centric tokenization optimization really comes in. While the full character set is large, the active vocabulary that's used for highly efficient tokenization is strategically controlled.
So they don't use all of them?
Not for the primary tokenization, no. Researchers found that models often only need to prioritize the top, say, 7,000 to 10,000 most common characters and their high-frequency compound pairings. For rare or specialized characters, the tokenizer can fall back to character-level encoding or even BPE-like structures.
So they're getting the best of both worlds.
They're leveraging the logographic structure only where it provides the maximum density gain, which mitigates that potential sprawl of the embedding layer.
So the engineers aren't just using hanzi, they are strategically optimizing the tokenizer to treat these common characters and compounds, these sequences of 2 or more hanzi that form new concepts, as ultra-efficient single or double tokens. And that's the key to overcoming the alphabet's inefficiency.
And this results in the core technical metric we found in the sources. Studies and benchmarks consistently show Chinese text requires 30 to 40% fewer tokens than English to convey the same content or complete the same reasoning task.
Okay, let's dedicate some time to the technical implication of that 30–40% reduction. Specifically in the attention mechanism, how does that translate into practical GPU savings?
The technical implication is immense, especially when you're talking about production inference, the moment the model is actually generating a response for a user.
Right.
In that ON calculation, cutting n by, say, 35% reduces the required floating point operations by approximately 58%.
58%.
Which means for every single query, the model requires almost 60% fewer calculations just related to attention mapping.
That's a massive throughput gain. You could serve almost twice the number of concurrent users on the exact same computational cluster.
Precisely. And what's more, because the KV cache, that's the memory footprint required for the model to remember past tokens in the context window, is also proportional to n. A 35% smaller sequence means 35% less VRAM consumed per user.
Which allows firms to pack more concurrent users onto each high-end GPU.
Or, and this is critical, to use mid-range, domestically available GPUs more effectively, avoiding that reliance on constrained Western hardware.
So this technical optimization isn't merely a language difference, it's a computational compression factor that's embedded directly into the input structure, and it drastically reduces the baseline workload on the transformer architecture itself.
It's a linguistic machine learning hack, really.
It really is.
And it's an advantage that begins even before the calculation starts. It's a reduced, optimized instruction set that fundamentally changes the economics of scaling an LLM.
So the theory of logographic compression is really compelling, but where do we see this advantage actually manifest in the real behavior and performance of the models? The sources provide some highly compelling proof points here.
They do, especially when the models are struggling with complex, intricate tasks.
Right.
The most robust evidence comes from these rigorous testing environments that demand complex reasoning, what we often refer to as chain-of-thought prompting.
Cody.
Coteen requires the model to generate extensive internal steps before it arrives at a final answer. And this is where the cumulative efficiency of compression should really shine brightest.
So let's revisit that specific finding involving the Qwen models on math problems. This is where we see that efficiency translating directly into performance superiority.
The analysis of the Qwen series tackling these complex mathematical and logical problems showed that Chinese chain-of-thought reasoning achieved not only higher accuracy, but it did so using only 61% of the tokens required for the English equivalent to complete the exact same reasoning task.
61%. They used less than 2/3 of the computational steps.
It's a staggering 39% efficiency gain directly linked to successful problem solving. But the critical finding was about the difficulty of the problems.
Okay, what did they find?
The analysis showed that the token gap widened significantly for the harder multi-step problems.
Oh, that's really interesting. Why would that be?
Well, think about it. Harder problems require longer, more intricate, and often recursive internal thought chains. So if the model is processing those internal chains using the structurally compressed language like Chinese, that cumulative efficiency gain, that 39% saving, is amplified with every single additional necessary step in the reasoning process.
So the logographic structure isn't just saving space for the simple input. It's making the most computationally intensive part of the whole process, that complex, sustained internal reasoning, significantly cheaper.
And potentially more reliable.
How so?
Well, the compression ensures that the critical context within that internal thought chain stays dense and manageable. This potentially reduces the chance of context drift or, forgetting key intermediate steps over a very long sequence.
Which is a common failure mode in LLMs with these huge context windows.
Exactly. The structural compression actually stabilizes the reasoning process itself.
Now, let's dive into what I find to be the most fascinating behavioral curiosity that researchers have observed, this phenomenon of spontaneous language switching.
It's genuinely remarkable.
It's almost as if the models are aware of their own computational cost curves.
It really looks like that. Researchers noted that highly capable multilingual LLMs, and even those that were predominantly trained on massive English corpora, sometimes spontaneously switch their internal processing language to Chinese.
Even if the prompt was in English.
Even if the user instruction was in English, but only when confronted with a really challenging, complex reasoning task.
So why would a sophisticated algorithm, given an input in one language, effectively decide to do its thinking in another language?
The technical interpretation is that it's purely an optimization-driven choice. Researchers who were observing models like Qwen and DeepSeek concluded this isn't random. The model is effectively choosing the path of least resistance.
Because it knows the Chinese tokenization path is cheaper.
It allows for denser, more efficient internal processing. By translating the complex parts of the problem into compressed hanzi, it reduces the token overhead required for these intricate tasks, making the processing itself cheaper and faster to execute.
It's like finding a compiler that automatically switches to optimized machine code for specific resource-intensive functions, even if the main program is written in Python.
That analogy is highly accurate. The model is leveraging the linguistic advantage of hanzi as a temporary, high-efficiency internal representation. It calculates the necessary matrix operations more economically in the compressed hanzi form, and then it translates the final output back to the required target language.
Which is often English.
Often English, yeah.
And this leads directly to the architectural choices of Chinese firms. It just stands to reason that Chinese-developed models are explicitly designed to maximize the structural advantage from the ground up.
They absolutely are. Alibaba's Qwen series, for instance, shows demonstrably superior token efficiency, specifically in Chinese benchmarks. Their entire architecture, from the tokenizer training data all the way to the internal processing pipelines, is optimized to leverage this logographic density.
So that design focus allows them to sustain longer effective context windows at a much lower marginal computational cost.
Right, and let's clarify what effective context window means here. Because if a Western model and a Chinese model both advertise a 100K token context limit.
The Chinese model is functionally superior because of its input efficiency.
Precisely. If the Chinese model can pack 40% more actual semantic information, more concepts, more facts, more relationships into that same 100K token limit because of superior input encoding, then its usable intelligence is dramatically higher.
The maximum token length might be the same,
But the information density processed per dollar and per watt is far greater.
and this research finding that non-English logographic languages can enhance token efficiency, it just runs directly counter to the initial assumptions that governed early LLM development.
It's a total paradigm shift.
Yeah.
I mean, earlier development was heavily biased toward English data and English-centric architectures. It led many to just assume English was the optimal language because of the sheer abundance of data and the ease of BPE tokenization.
But now we know better.
Now we are seeing papers on cross-lingual reasoning that explicitly challenge this. Far from being a niche, logographic systems are proving to be a genuine asset for fundamental computational efficiency.
And some Chinese researchers are even arguing that the symbolic precision inherent in Mandarin accelerates training convergence and improves overall model stability.
That's the argument. It suggests that the alphabet, while it's flexible and globally ubiquitous, creates this unavoidable signal-to-noise problem for transformer architectures.
Too much noise in the form of fragmented subwords for a specific concept.
That's the core of it. The model receives cleaner, more compact data points representing complex concepts right from the beginning, which leads to less noise and better initial training efficiency.
Okay, let's zoom out. A 30 to 40% efficiency boost in token usage isn't just an interesting linguistic curiosity. It translates directly into massive strategic and economic leverage.
Especially critical for Chinese firms that are operating under specific, intense geopolitical constraints.
Right. The link between this linguistic advantage and geopolitics is probably the most critical element of this entire deep dive. Lower token counts fundamentally mean reduced compute requirements.
For both training and, maybe more importantly, for deployment. This is vital because Chinese firms are operating under severe limitations imposed by stringent U.S. export controls on advanced semiconductors.
We're talking specifically about the controls placed on high-end GPUs like NVIDIA's A100s and H100s, which are, the gold standard for LLM training.
Exactly. Those controls create an artificial scarcity and a high cost ceiling for top-tier compute. Chinese firms cannot simply throw unlimited compute at the problem in the way their Western counterparts theoretically can.
So they have to be more efficient.
They have to maximize intelligence per watt, the ability to train and deploy highly capable models more cheaply, using less of that raw, constrained compute power, provides a significant, tangible strategic advantage.
It's the ultimate cost fraction optimization. They're forced by external constraint to operate closer to the theoretical maximum efficiency for their available hardware.
And they often rely more heavily on domestically produced chips, like those from Huawei or Ascend, which might be a generation or two behind in raw processing power.
But the linguistic efficiency acts as a multiplier.
It does. It acts as a multiplier on their constrained compute resources. If they use a 30% less powerful domestic chip, but their linguistic encoding is 35% more efficient, they can often meet or even exceed the performance benchmarks of the Western model that's using the constrained top-tier chip.
Which helps explain why China's open-source offerings often match or exceed Western closed models while using just a fraction of the inferred costs.
They are essentially circumventing the hardware bottleneck through a software and linguistic optimization layer.
And this advantage wasn't just an accident, it's the result of highly focused optimization.
Right. Companies like Alibaba, Baidu, DeepSeek, they didn't just gather Chinese text data. They leveraged these vast troves of high-quality native hanzi texts billions of documents to strategically optimize two core components.
The tokenizers and the architectures themselves.
Exactly. They designed them specifically for linguistic density.
So they customized the tool for the most efficient language structure rather than trying to force the efficient language into a generalized tool that was built for the alphabet.
Precisely. They engineered systems where the models reason optimally within their native linguistic framework that compressed hanzi structure and then translate effectively for multilingual interaction when they need to. It maximizes knowledge density and speed before the final output stage.
And this optimized system translates directly into market dominance.
It does, particularly in their home territory and globally in open source adoption. The sources mention a very clear inflection point.
When was that?
China overtook the U.S. in cumulative open model downloads in 2025. That shows incredibly rapid adoption. Furthermore, the efficiency gains translate directly into better real-world deployment metrics within China's massive, high-speed digital economy.
So tell us how this efficiency creates a virtuous, self-reinforcing loop in their domestic digital ecosystem. We're talking everything from search to ubiquitous chatbots.
This is where the structural advantage really compounds. China has this vast domestic market across all digital services, so deploying faster, cheaper inference in Chinese for these large-scale applications leads to a self-reinforcing virtuous cycle.
Cheaper inference means broader deployment.
Broader instant deployment to hundreds of millions of users. Broader deployment generates exponentially more user interaction data. More data allows for superior, highly optimized fine-tuning and improvement of the models.
And that improvement compounds the initial linguistic edge. So the logographic compression makes their models cheaper and faster to train, which leads to wider deployment and more data, which makes the next generation of models even better and cheaper to run.
It's an exponential feedback loop.
An amplification loop driven entirely by input efficiency.
It is. And crucially, the technical argument suggests this advantage isn't static. It grows with scale. As LLMs inevitably continue to grow larger and context windows become exponentially longer, say, pushing beyond 200,000 or 500,000 tokens, the token density advantage will only amplify in its impact.
Because if the sequence length n continues to grow and the computational cost scales quadratically, then a 35% reduction in n before the calculation even begins yields these massive nonlinear savings that become strategically priceless.
The competitive race is no longer just about who can build the largest model. It is fundamentally shifting toward maximizing intelligence per watt and per dollar. And in that metric, the logographic compression inherent in hanzi proves to be an increasingly powerful and strategically critical technical advantage.
Leveraging an ancient writing system to provide a profound modern computational shortcut, it's incredible to think that the structure of a language developed over millennia is now dictating the cutting edge of artificial intelligence cost curves.
It really highlights how deeply interconnected these systems are and how much performance can still be squeezed out of existing architectures simply by optimizing the input encoding.
This has been a genuinely deep dive into how fundamental linguistic structure shapes the cutting edge of computation and strategy. Let's quickly summarize the core technical takeaways for you, the learner.
Okay, first, LLM supremacy hinges heavily on input efficiency, not just on scale. The logographic nature of hanzi means each character carries immense semantic density, which directly contradicts those earlier assumptions about alphabetic superiority.
Second, this density provides a quantifiable form of data compression. It results in a 30 to 40% reduction in the token count compared to English for the equivalent information, which is just a massive engineering win.
Third, this compression directly and nonlinearly reduces computational costs through that ON attention mechanism. And this efficiency is so powerful that models sometimes spontaneously switch to Chinese internally just to optimize complex reasoning tasks.
And finally, amid severe global chip constraints, this structural advantage allows Chinese firms to train and deploy highly capable competitive models at a lower relative cost, accelerating their convergence with Western performance metrics and fueling a powerful, efficient domestic ecosystem.
Understanding this structural advantage is crucial for anyone who is monitoring the AI landscape. It demonstrates that foundational architectural decisions, particularly tokenization methods, are now being fundamentally shaped by linguistic variables, creating a powerful, sustained competitive moat.
And it raises a profound question that takes this technical premise one step further. If the computational cost of language processing, that token bottleneck, is the primary friction point for scaling, should future globally competitive LLMs attempt to abandon natural language tokens entirely?
Should we ditch BPE and standard character encoding for an internal, purely symbolic and hypercompressed intermediate thought language, a universal logographic machine code designed solely for maximum reasoning efficiency.
Regardless of what the user inputs or what the model outputs,
Yeah.
that is the logical extension of the efficiency we've discussed today. Creating a new, optimized language for the machines themselves. Something truly provocative for you to mull over as you see these models continue their inexorable march towards scale.
Thank you for joining us for this Neural Intel Deep Dive.
If you want to stay updated on the latest in AI and ML, visit our webpage, neuralintel.org, and check us out on YouTube for more technical deep dives. Until next time.